Okay, so this is problem 1 on homework 8, so 13.7, both parts. Part A says derive the expression for x, the steady state amplitude of motion of the mass m, and it gives us this, this diagram here with a spring, and it gives us x and y as the inputs, and here I simply just drew the free body diagram with the forces and the different directions, what we did from the first half of the semester, and then we get our equations over here. So we have mx double dot equals f1 minus f2, and if you combine these three equations, you'll get our main equation. So mx double dot plus cx dot plus cx equals cy dot, and using the Laplace the transform, we'll get this expression here, and it's simply just ms squared plus cs plus k equals xs or times xs equals cs times ys. I originally put the parentheses here and I realized it was wrong, so that's what that is. And then the transfer function that comes out of it would be xs over ys, and you get cs over ms squared plus cs plus k. And you're given this expression here, and you know that for x it's going to be about the same, but it'll have a different amplitude, which is what we're trying to find, because this becomes the steady state, and then plus a phase shift of phi. And we know that the two amplitudes, so the steady state, which would be capital X over the given one y, those x over y will give you, or is equal to, the magnitude of the transfer function when you substitute s for j omega, and that's what this expression here is. So you have the magnitude of the numerator, which is just c omega j, and then over the magnitude of the denominator. And this k minus m omega squared looks a little weird, but it's from the s being squared, so when you square j, it becomes a negative, so that's where we get, and then we move the k over to only have two components, I guess. So you get k minus m omega squared plus c omega j, and the magnitude of that. You come down here, and you'll get c, the magnitude of the numerator will just be c omega, and then the magnitude of the denominator will be the square root of k, of the quantity k minus m omega squared, that's squared, plus omega c squared. And then we want to manipulate this equation to make it more useful for us. So you want to divide by m here, because we want, essentially we want to try to get omega by itself. And then you want to multiply c by 2 times the square root of mk over 2 times the square root of mk, because as I noted over here, zeta y, which shouldn't be confused with the y up here, is actually c over 2 times the square root of mk. So if we can simplify our equation, it'll look much nicer and make it more easy to use. So we can do that here and here, and then finally we want to divide by k, because if we divide by k, we will end up getting an expression that will look something like this, and we'll be able to simplify it further, because the natural frequency omega n squared is k over m, or natural frequency is the square root of k over m, and then we'll be able to substitute that in. So you do that to both sides. That's what the 3 is saying. So divide top and bottom by k, and so that expression will look something like this, where you have c over 2 times the square root of mk times 2 times square root of mk times omega times 1 over k. And this expression can be zeta, can be simplified as zeta, and down here we can replace, since we divided by m here, we got a k over m, so we can put that as natural frequency squared. So we can substitute that, and then here we also have another c over 2 times the square root of mk, which is also zeta. And then the rest of the expression is just simplified and further shown there. And then once we do all substitutions, it will look something like this here. So we got 2y times the square root of m over k, which, if you remember, the natural frequency is square root of k over m. So here we can just signal this quantity as 1 over the natural frequency. And all of that over the square root of what we had last time simplified, but now we can substitute our m over k